Hello, my name is Andrew Moylan. This presentation is about one of Mathematica's unique strengths, the ability to use symbolic computation in numerical methods. Before I get into detailed examples, I'll first take a couple of minutes to give the big picture and explain why symbolic computation is so valuable in numerics. Then I'll talk about the first big advantage of symbolics for numerics, which is the ability to infer from the user's input which algorithms are suitable for solving their problem, instead of the user having to do this for themselves. Then I'll give a couple of examples of numerical methods in Mathematica that fundamentally rely on symbolic computation, and hence are impossible or impractical in any traditional numerics-only system. Finally, I'll talk about the benefits for performance that symbolics can bring. These include many automatic optimizations that Mathematica applies that you may never have realized were happening behind the scenes. So, why are hybrid symbolic numeric methods useful? I'm going to explain this by comparing the way traditional numeric systems view a numerical problem with the way Mathematica is able to view the same problem. By traditional numerical system, I mean any system with the usual firm separation between code that's written by the user on the one hand and runtime data and variables on the other hand. So this includes things like spreadsheets, numerical matrix systems, and programming languages like C and Fortran. So suppose you want to numerically compute an integral, such as this one, the integral from 0 to 3 of ceiling of x times Bessel J1 of 30x squared. Here's the fundamental limitation of all traditional numerical systems. To tell a traditional numerical system to do this integral, you would first write a subroutine to evaluate the integrand. Then you would pass the name or pointer of that subroutine to a numerical integration algorithm in the traditional numerical system. But that algorithm knows only the name of your function, and it has no idea what code is inside. From the point of view of the traditional numerical system, the function is basically a mysterious black box, and the only thing it can do with the black box is pass in values of x and get out the resulting function value, and try to build up a picture of the numerical problem in this way. The problem is that this blind numerical sampling often misses all the interesting or important features of the problem. You can see that for this integrand, blindly sampling the function hardly gives you any useful information at all about the overall shape or behavior of this function or its integral. Now let's compare this with how Mathematica views the same numerical integration problem. When you tell Mathematica to numerically integrate a function like this, the full structure of the integrand as a symbolic expression is available to Mathematica, and there's a lot of information in that expression. For starters, Mathematica recognizes the function ceiling of x and knows to therefore expect discontinuities at every integer value of x. Mathematica can deduce that Bessel J1 of 30x squared satisfies this differential equation, and from linear differential equations like this, it is possible to construct customized integration rules suitable for highly oscillatory functions. By inspecting the argument of the Bessel function, 30x squared, Mathematica infers that the specialized integration rule only needs to be used on the two rapidly oscillatory subregions of this problem, and not on the first subregion. And Mathematica compiles simple mathematical operations like these, ceiling of x, 30x squared, into optimized compiled functions for faster execution. All of the above things happen automatically behind the scenes when you use Mathematica's and integrate function on this problem. and they are the reason why Mathematica is able to confidently give the correct answer. So, the big advantage Mathematica has is being able to see the symbolic structure of numerical problems. In this talk, I'll show examples of how this information is used, beginning with intelligent method selection. I'll talk about converting numerical problems to standard forms, classifying problems and choosing a suitable class of algorithms, and identifying cases for which more efficient specialized methods can be used. A great example of automatic problem standardization is the function ndsolve for numerically solving differential equations. ndsolve lets you specify the set of differential equations and boundary conditions in a natural mathematical notation. In this case, the differential equation implicitly gives the second derivative y double prime. And in fact, because of this square root, there are two distinct branches or solutions to this differential equation. ndsolve obtains them both by first solving the implicit equation, converting it into these two explicit systems of differential equations. In this standard form, they are passed to a suitable ordinary differential equation integration algorithm. ndsolve handles many different types of differential equations, instead of requiring the user to learn the different syntax of a collection of specialized functions. Partial differential equations like this one are discretized and passed to an algorithm for integrating the problem forwards from the boundary condition. Differential equations combined with non-differential equations are automatically solved, rearranged into a standard form, and passed to a suitable differential algebraic equation solver. Likewise for delayed differential equations, in which even the initial history function is easily made a part of the set of differential equations and boundary conditions supplied by the user. Differential equations with boundary conditions at several different points look very similar to initial value problems, but they do require specialized methods. However, a user of ndsolve doesn't need to know this fact. In this example, because boundary conditions are specified at 3 different points, a standardized version of this problem is passed to a numerical shooting type method. In addition to interpreting and standardizing problems given in mathematically familiar notation, automatic method selection based on symbolic structure also gives every user access to expert quality methods. In numerical integration, highly oscillatory Fourier type integrals arise frequently in many applications. Because of this, a large number of very specialized integration algorithms have been developed for specific classes of Fourier integrals. Only a small number of experts are really familiar with all of these methods, but because Mathematica is able to symbolically recognize the special cases, even non-experts get the full benefit of these highly specialized methods. In a traditional numerical system, you would either need to be an expert in these methods, or more likely you would need to settle for whatever generic integration algorithm is recommended. This means getting slower and less accurate results. We can simulate this by manually choosing a general purpose algorithm instead of allowing an integrate to detect the special nature of this integral. Mathematica's nminimize function is a global numerical minimization function capable of dealing with a wide range of different objective functions and constraints. But some types of global optimization problems already have specialized methods and indeed whole fields of study devoted to them, such as linear optimization with linear constraints, as you see here, which are of course also known as linear programming problems. Suppose you're in a situation where the user interactively gives the function or the constraints, or they otherwise are somehow obtained externally from an unpredictable source. You may need to be able to perform a numerical minimization no matter which function or constraints are given, but if and when a linear objective function with linear constraints is given, you certainly want to use faster and more accurate linear programming methods on that particular problem. And this is exactly what Mathematica is uniquely able to do. Having talked about automatic method selection based on symbolic structure, I now want to give a couple of examples of actual numerical methods that use symbolic computation. The examples I'll show are two methods or submethods from Mathematica's nintegrate function. The first example is about the handling of piecewise or discontinuous functions in numerical integration, and the second example is about the construction of customized integration rules for highly oscillatory integrals. So, first let's see why piecewise functions have always been, and still are, a problem for traditional numerical systems. Here's a very simple piecewise function, equal to x over 2 when x is less than 3, and equal to 2 over x otherwise. Suppose you want to numerically determine the integral of this function, the shaded area. A traditional numerical method can only do one thing: numerically evaluate the integrand. But getting an accurate estimate of this integral requires accurately knowing the location of the jump discontinuity at x equals 3. So an adaptive numerical sampling process needs to repeatedly subdivide and sample closer and closer together in order to accurately model the behavior of the function near the problematic point, x equals 3. In this example, a traditional integration method obtains an error of about 5 by 10 to the minus 4 after over 200 evaluations. And that's a pretty disappointing result for what is in effect a very simple function. Down here, by plotting the location of each sample from top to bottom, you can see the traditional blind numerical method repeatedly subdividing and sampling closer and closer to x equals 3 as the algorithm proceeds. When Mathematica solves the same integration problem, the structural dependence on the condition x less than 3 is detected, and nintegrate uses this information to split the integral at x equals 3. On the resulting two subregions, the integrand is completely smooth, and in this case, general purpose integration rules are very efficient. The end result is that only 44 sampling points are required to get a result accurate within an error of 3 by 10 to the minus 14, which is far superior to the example we just saw using a traditional blind numerical method. A plot of the location of each sample shows that nintegrate first took a few samples in each subregion, then made, in this case, just one subdivision on one of the integration regions, before obtaining a result with a sufficient level of confidence. Let's take a look at how far this piecewise subdivision can go and how it works. In this integral, the integrand is the sign of a piecewise function. The piecewise function is the min of a linear and a quadratic function of x. Mathematica knows how to resolve this min into subregions on which either the first or second argument is the minimum. After this decomposition, nintegrate is left with these three subregions, and on each of these subregions, the integrand is simplified into one of the two cases of the min. And on each subregion, the integrand is completely smooth, and general-purpose integration rules can therefore operate very efficiently. Piecewise subdivision applies equally well in multi-dimensional cases. In this two-dimensional integral, we use the bool function to obtain an integrand that is equal to 1 plus cos of 4xy on regions satisfying this predicate and 0 anywhere else. The region corresponds to a slice through an elliptical annulus, and the integral computed by an integrate, about 1.497, is the volume of the shaded area beneath this plot of the integrand. This integrand is discontinuous at every point on the boundary of the region satisfying the predicate. Using a cylindrical decomposition and other symbolic methods, Mathematica is able to break up the predicate into these 6 distinct regions on which the integrand is non-zero. In each region, x is restricted to a specific numerical range, and y is restricted to a range that depends on x. Here's a visualization of the 6 subregions Mathematica uses to compute this integral. In this form, a multi-dimensional integration rule can be applied, although we'll see later in this presentation that there is a further symbolic optimization that an integrate performs on each of these 6 subregions. The second example I'll show in this section also concerns a class of integrals that have always been difficult or impossible for traditional numerical integration methods, namely highly oscillatory integrals. Highly oscillatory integrals arise often in applications, and they are important enough that in one well-known collection of numerical challenge problems, the first problem was this numerical integral. This is a plot of the integrand. Note that it oscillates an infinite number of times in the interval from 0 to 1. Although when this challenge was posed, this was a difficult problem requiring individual analysis, this integral now falls under a broad class of oscillatory integrals that are automatically solved by an integrate, as you see here. For these integrals, an integrate uses what is called a Levin-type integration method. These methods work by approximating the integrand using a more suitable set of basis functions than traditional general-purpose integration methods. In all general-purpose integration methods, such as Newton, Gaussian, or Clenshaw-Curtis quadrature, the integrand is essentially approximated as a polynomial. That is, it's approximated as the sum of basis functions like x, x squared, x cubed, shown here. In a Levin-type integration method, a different and better suited set of basis functions is used. The Levin basis functions are derivable from a linear differential equation satisfied by the oscillatory part of the integrand, if that differential equation exists and can be found. For this numerical integration, an integrate symbolically determines that the oscillatory part of the integrand satisfies this system of linear differential equations of order 2. In this plot I've shown a few of the basis functions that are used by an integrate when computing this numerical integral using a Levin-type method. You can see that unlike the monomial basis functions of a general-purpose integration rule, these basis functions bear a strong resemblance to the shape of our integrand, and in fact they make the integration very efficient. I won't go into every detail about how Levin-type methods work in this presentation, but please do take a look at the advanced documentation tutorials for an integrate if you'd like to learn more. Here's another example of an integrand for which we can construct a customized Levin-type integration rule. And here is the 14th order linear differential system, written here in matrix form, that Mathematica derives and uses for this integral. Now, in the previous example, it's conceivable that you might separately derive the second order linear differential equation and then manually code up a Levin-type integration rule for that specific integrand. But it's completely impractical to try to do that every time a different oscillatory integration comes up, especially in symbolically difficult cases like this one. And so for Levin-type methods to be useful as a general tool, you need a system in which both the difficult symbolic derivations and the heavy number crunching can both be done automatically for the user. It's interesting to take a quick look under the hood at an intermediate stage of Mathematica's processing of an oscillatory numerical integral. Using the internal function Levin integrand reduce, we find out that for this integrand log x plus Fresnel s of square root x over x, an integrate has identified an oscillatory function satisfying a third order differential equation, and using the rules property of this Levin integrand data structure, you can see the decomposition in more detail. There is an additive term, a multiplicative amplitude term, then there is the third order differential equation represented in matrix form, with the oscillatory function and its derivatives in this vector. For a more complete description of the Levin integrand data structure, see the advanced documentation tutorials for an integrate. You may recognize differential root reduce as one piece of symbolic machinery likely used by Mathematica in the hybrid symbolic numeric method I've just described. Differential root reduce is used to obtain special functions like Fresnel s in differential root form, which is essentially a representation as a linear differential equation with boundary conditions. Differential root reduce was introduced in Mathematica 7, and it was very important in making possible the development of general Levin-type integration rules in Mathematica 8. Each new development in Mathematica's symbolic engine opens up new possibilities for intelligent method selection and for hybrid methods in Mathematica's numerics functions. The examples I just showed are two out of several unique numerical methods and pre-processing stages in Mathematica. There are many more examples in n-integrate and other numerics functions, and many more again throughout the wider system, including advanced solvers in areas like probability and statistics, control systems, and many other areas. So in this final section, I'm going to show a couple of ways in which symbolic computation enables automatic optimization. First, I'll talk about the optimizing compiler, then about the symbolic computation of derivatives, which are useful in many numerics functions. Finally, I'll give an example of transforming a problem into a different form in which it can be more efficiently solved. You may well be amazed to learn how often Mathematica automatically compiles your input without you ever needing to know about it. When you use functions like table or map to construct lists, or in just about any numerical function, Mathematica compiles your input function if possible and if it makes sense given the size of the problem. In this ND-solve example, after standardizing the problem, including solving these equations for y prime of t as a function of y and t, Mathematica effectively compiles the function like this. The compiled function contains fast, low-level instructions and evaluates many times faster than regular Mathematica code. The compiler also performs optimizations, as you can see here. The expression y squared minus cos y squared contains the sub-expression y squared in two different places. Mathematica detects this fact and introduces a temporary variable, here called compile 404, to ensure that y squared is only computed once. In this example, the gain may be fairly small, but common sub-expressions like this come up surprisingly often in real situations. For example, take a look at the Hessian tensor of this vector field. There are repeated sub-expressions all over the place, and when Mathematica compiles this tensor expression, it's able to greatly reduce the total number of low-level operations that take place. This is the resulting compiled function. You wouldn't want to have to perform this kind of optimization manually, but Mathematica is able to do it for you because it has access to the symbolic structure of your input function. Many numerical algorithms, especially in the area of optimization and root finding, perform much better if they have access to the derivatives of the functions being solved or optimized. This is because, in the case of minimization, the algorithms essentially need to roll downhill towards the local minimum. And the derivative tells you which way is downhill. In this particular example, Mathematica applies a quasi-Newton method that takes advantage of the gradient of the objective function. The gradient is easily and automatically computed from the symbolic structure of the input using the Mathematica function d. This diagram shows the steps of the minimization algorithm over a vector plot of the gradient field of the objective function. Here's another example. Root finding algorithms use the Jacobian to move towards the location of a nearby root. In this four-dimensional root finding problem, the Jacobian is this moderately large expression. Now, in a traditional numerical system, for efficiency, you may be well advised to manually compute this Jacobian matrix and then code a subroutine by hand that creates and returns this matrix for any value of the arguments x, y, z, and u. Then you would pass that function, or a function pointer, along with your original objective function, into the root finding algorithm. That's the theory, but in practice, most of the time the user isn't going to bother going to those lengths, especially when they're in the early stage of developing or exploring new ideas. And this means that, in practice, gradient information is usually not available in traditional numerical systems, and you'll find that these systems normally rely by default on less powerful generic methods that don't require any information about the derivatives of the input function. Or they may obtain the derivatives by finite difference sampling, which enables the use of derivative-based methods, but it's slower and less accurate than having direct access to the exact symbolic form of the derivatives. In Mathematica, the necessary derivatives are computed automatically behind the scenes, and they're compiled, of course, as an added bonus. As a final example of an optimization that relies on symbolic computation, consider the piecewise subdivision example we saw earlier. In this example, the integration region was subdivided into 6 pieces. Let's look at one of the integration subregions, this one highlighted in green. If an integration region is square or rectangular, Mathematica can use pre-computed coefficients and weights to estimate the integral, and this saves time. Therefore, it would be convenient if we could transform our existing integrand and integration range into a new integrand with an integration range that is a unit square. This is done using a change of variables, as usual in calculus. You may recall that a change of variables involves multiplying by the derivative of the Jacobian of the variable transformation. But of course Mathematica has that part covered, and in the end, for this particular subregion, it turns out that this is the final integrand that Mathematica obtains for numerical integration. The original integrand was cos 5xy plus 1. So it's a different integrand on a different integration region, but the value of the integral is the same. The price of the change of variables is, of course, that this integrand is quite a bit more complicated. But this is not as big a problem as it may seem. This expression is compiled automatically by Mathematica, and as you can see, there is a preponderance of repeated expressions and sub-expressions throughout this expression. Just look at how many times expressions like square root 3 or square root 3 minus 2 appear and reappear. Mathematica transparently applies this unit cube rescaling method to all 6 of the integration subregions without the user needing to know anything about it. Thanks for attending this presentation about the unique advantages symbolic computation brings to Mathematica's numerics functions. On this final slide, I've finished with a quotation that sums up the feeling about symbolics and numerics inside the halls of Wolfram Research. I asked Darren Glossmeyer about hybrid methods in his work as lead statistics developer, and his reaction was, "I'm so used to mixing numerics and symbolics, I generally don't even think about it." In other words, hybrid symbolic numeric methods are the norm rather than the exception in Mathematica.